1956, AT&T laid the first transoceanic cable called TAT-1. But the only ship suitable for such long distances was the British cable ship Monarch, which AT&T had been chartering since the early 1950s. And to lay TAT-1's modern telephone cables, all of the machinery on the Monarch required extensive modifications. It was clear AT&T needed its own ship. So the company designed the first truly modern cable ship, the CS Longlines. It was launched in 1961 and by 1963 had made its maiden voyage, laying the third transatlantic cable, TAT-3. On its next journey, the ship laid TPC-1, the very first Transpacific cable. That run is documented in this film. Over the next 2 decades, CS Longlines would install over 40,000 miles of cable around the world. By the 1980s, plans were made for the very first fiber optic transatlantic cable, TAT-8, and Longlines was the ship for the job. On one early test of the new technology, technicians hauled up the cable after they found a short in the system and discovered shark teeth embedded in the cable. Turns out the unshielded fiber optic cable caused an electrical field that drove the sharks into a feeding frenzy. There are just some things you can't test for in the lab. CS Longlines completed laying TAT-8 in 1988. For another decade or so, the ship served AT&T, laying other cables and making repairs. From the great ship's heyday, here's CS Longlines.
Cable number 3 is ready for service. We have 2 order circuits patched in and working perfectly.
Wonderful, Wiedemann. That's what we've been waiting for. Thank you very much.
You can get some sleep now. Cheerio.
You know, I think we'll do that. Thank you again. Good night. Well, that's your works. Yeah.
2 people talking via ship-to-shore radio telephone. One on the high seas and the other on the Cornish coast of Great Britain. It sounds commonplace, and as a matter of fact, it is. But behind this particular conversation is a fascinating story. The construction of a worldwide network of underseas telephone cables. I am Lowell Wingert, a vice president of the American Telephone and Telegraph Company. And my job involves me in the continuously unfolding drama of international communications. The incident you have just seen took place in September 1963 aboard the Bell Systems ocean cable layer, CS Longlines. Only a few minutes before, engineers aboard ship had completed the final splice of a third transatlantic telephone cable. Then came the radio telephone call confirming completion of still another communications route between the United States and England. It was an historic moment, and one that has been repeated a number of times on the CS Longlines. A ship that has played an important role in expanding communications throughout the world. This is her story, the story of a ship.
November 1963. Once again, the Bell Systems ocean cable layer CS Longlines moves up Chesapeake Bay toward Baltimore. She is returning with pride after her first big job, a third transatlantic telephone cable. This latest voice route to Europe extends 3,500 miles along the ocean floor, from the beaches of New Jersey to the coast of Cornwall on the southwestern tip of England. The manufacturing plant is our starting point for this fascinating project. Underseas cable designed by the Bell Telephone Laboratories is manufactured not only at the Western Electric plant in Baltimore, but also at 2 other identical cable plants, one in Southampton, England, and the other in Yokohama, Japan. Cable at all 3 plants is made to Bell System design specifications. In the first step on the assembly line, 41 fine steel wires are wrapped together on a stranding machine to provide an inner core, which gives the cable its required tensile strength. Next, the inner conductor, which is one of two conductors in this coaxial cable, is formed by wrapping a strip of copper tape around the core of steel wires. Its seam is electrically welded. A layer of polyethylene is added as insulation between the inner and outer conductors. Transparent at first, it becomes white as it is cooled by water. This insulating layer is then shaved to meet rigid engineering tolerances. Now an outer copper sheath, which serves as the second conductor of the coaxial cable, is shaped around the white polyethylene layer. Finally, a protective covering of black polyethylene is added, and the manufacturing process is complete. The finished cable is 1 1/4 inches in diameter. Its 5 separate layers each represent a distinct and precise manufacturing technique. In Baltimore, as in other plants, the new cable is placed in large pans, each holding about 20 miles of cable. These pans are then towed to a loading platform at dockside. The cable ends are terminated in bell-shaped couplings, which are tied together with a metal bar, then wrapped in canvas to aid their passage along the loading route. The deck is notified, the transporter turned on, and another cable section starts aboard. Up through the bell mouth, along the trough, the coupling moves as cable starts paying out of the new storage pan. Cable from 2 pans is pulled aboard simultaneously. It follows a carefully planned route as it wends its way aboard ship and into cable tanks deep in the hold. A transporter pulls the cable aboard at speeds of 4 to 5 miles an hour. Down it goes through a slot in the deck and into the cable tank, where it is neatly coiled. One man guides the cable around the center core. Other workers make certain it falls tightly into place. Fully loaded, CS Long Lines will carry some 2,000 miles of cable in her 3 storage tanks. As the cable loading continues, repeaters, each weighing 500 pounds, are hoisted aboard ship. Some 275 of these voice amplifiers will be used between Hawaii and Japan. Below deck, they are stored in the proper order for splicing between cable sections. The ends of each 20-mile section are secured opposite the repeaters to which the cable will be spliced, while the remainder is coiled in the cable tank below. The bights, or cable ends, running in and out of the tank are secured to the tank wall, where they are held in place until the cable feeds out during the laying operation. Technicians join the end of each section to its proper repeater. The end of each repeater is covered by a plastic disc to protect the connectors during shipment. This shield is removed, and the connectors, or pigtails, are prepared for splicing. The larger pigtail will be spliced to the center conductor of the cable, while the smaller will be spliced to the cable's outer sheath. A new insulating cover of polyethylene is molded over the splice. The finished joint appears as a slight bulge in the polyethylene insulation. Each splice is x-rayed and carefully examined to make certain that no imperfection exists. When the splice is completed, the cable coupling is moved into position for joining to the metal case of the repeater. It is precisely fitted and then bolted down securely to withstand the extreme tension encountered on its trip to the ocean floor. With her cable tanks full, all cable ends secured, and all repeaters spliced in along the entire length of the cable, the CS Long Lines puts out to sea. Destination, Hawaii. The beginning point of the cable to Japan is the underground terminal station at Makaha Beach on the island of Oahu. Here, a short section of armored cable is pulled ashore to the terminal. This shore end section is then spliced to the 2,000 miles of deep-sea cable aboard ship. Now the long lines moves out toward Midway Island, some 1,300 miles to the northwest. As she starts to work, signals flying from her mast say to all other ships, "Cable laying underway. Please stand clear." Now the miles of cable so carefully loaded in Baltimore uncoil upward to the deck above. Passing through the uprunner slot, the cable moves toward the stern of the ship, where it travels out the chute and disappears into the sea. While each 20-mile section is being laid, the next repeater is readied for its trip overboard. An electric hoist is used to lift the repeater from the rack and lower it into the cable trough. A parachute is attached to the heavy repeater so that its sinking speed will match that of the lighter cable. As the end of a cable section is reached, the cable ends attached to the tank wall pull free and start the repeater through the tractor-like treads of the linear cable engine. Then out the stern chute and down into the sea. A few seconds after it disappears beneath the waves, a balloon pops to the surface, indicating that the parachute covering is pulled off and the chute has opened. Now the repeater gently sinks to the ocean floor. Its descent is so gradual that the long lines may travel another 15 miles before the repeater settles on the bottom of the sea. And so, under the watchful eyes of experienced technicians, the cable continues to pay out mile after mile and repeater after repeater. A ship's officer using a sextant is shooting the sun for a position check. Similar checks are made daily at dawn and dusk using visible stars. These periodic position checks aid the captain in his task of accurately plotting the pre-planned course his ship must travel. The route the ship follows is one which was carefully planned through oceanographic surveys. The nerve center of the cable laying operation is the drum room, where every phase of the project is observed and controlled. Fathometers and depth recorders provide a picture of the ocean bottom beneath the ship. Each detail is recorded to determine the amount of slack needed so that the cable will conform to the contours of the ocean floor. When any unexpected conditions arise, the engineers who laid out the system are on board to make any changes necessary in the cable laying plan. At the central control console, continuous readings are made of the ship's actual speed over the ocean floor. Here also, the cable payout rate of the linear engine is controlled. A small computer is used to automatically compare and then control these variables properly. Detailed records are kept of the cable laid, tension on the cable, and many other statistics. Transmission men continuously conduct tests with the distant shore terminal. Test signals are transmitted through all the cable aboard ship, as well as the cable which has been laid between the ship and the shore terminal. These tests ensure that all repeaters and cable sections are working satisfactorily, and that transmission performance measures up to engineered standards. Careful check is maintained on the power supply to the repeaters aboard ship and those on the ocean bottom. 5,000 volts are required to operate the vacuum tubes in all the repeaters along the route. Telephone circuits are established over the cable so that the ship may maintain communication with the shore terminal and coordinate all tests and operations. And so the job goes on, with technicians and ship's crew performing the numerous tasks required to keep the cable laying operation in motion. The work continues around the clock and in all kinds of weather. At Midway Island, the cable is brought ashore to provide communications to this Pacific outpost. The rough coral reefs surrounding Midway and other Pacific islands can sometimes damage even heavily armored cable, so here it is necessary to provide the cable with additional protection. Using balloons to aid them in moving the cable to its proper position, the divers fit a heavy armor pipe around the cable to protect it from the coral heads and jagged rocks along the route. This armor casing is extended out over the reef to a depth of 100 feet or more, where the cable plunges over the coral cliff toward the ocean bottom, nearly 3 miles below. From Midway, the long lines continues along her route to a point 700 miles west and the end of her 2,000-mile load of deep-sea cable. Here, a large marker buoy is readied for attachment to the cable end. Before it goes overboard, a radar reflector is mounted on the buoy as a navigation aid in finding the spot at a later date. Now securely anchored and lashed to the cable end, the buoy and its floats will be pulled up when cable laying operations are resumed. Leaving the marker buoy, the long lines proceeds to Honolulu to rendezvous with the cable transport Arthur M. Huddle. Here, cable manufactured in England is transloaded into the long line storage tanks. Departing Honolulu, the long lines returns to the area where the buoy was dropped. The radar reflector atop the buoy makes locating its position routine. Once the buoy is sighted, the engines are slowed for the approach and pickup. The floats and buoy are recovered, and then the cable end is hauled up from the ocean floor for splicing to the new load of cable aboard ship. The splicing is completed below deck in the joining room. The cable ends have been prepared for splicing by stripping back the black protective covering, the white polyethylene insulation, and the inner conductor to expose the center core of steel strands. These strands and the inner copper conductor are inserted into a heavy steel sleeve, which is crimped together by a 500-ton press to form a strong splice. Next, the white polyethylene plastic is molded around the splice to form a continuous insulation between the two conductors. Each molding is x-rayed and the picture examined for any imperfection in the joint, which might affect the quality of transmission. If the mold is perfect, the splice is completed and closed. Continuing westward over the Pacific wastes for some 400 miles, the cable is brought ashore at Wake Island to link this tiny dot to the U.S. mainland. And then on to the cable terminal at Guam and the end of her second load of cable. From Guam, the long lines moves up to Yokohama for another load of cable, which has been manufactured in Japan. Here also she picks up repeaters which had been previously shipped awaiting her arrival. Trucks carrying these repeaters form a colorful convoy as they wind their way through the streets of downtown Yokohama on their way to the docks. The cable is transported from the plant in barges, which are towed to the ship. From the barges, the cable is drawn in over the bow of the ship into its tanks. Here, too, the cable is neatly coiled in the cable tank by Japanese workers. The cable loading continues around the clock through the night. Moving down the coast, the long line stands offshore at Ninomiya, the Japanese cable terminal. To avoid cable damage in the shallow waters, balloons are attached so that it may be floated ashore. As the cable pays out, the ship's workboat starts pulling it toward the beach. A half-mile offshore, the cable is attached to a steel hawser, which has been floated out to meet the workboat. The cable is gradually pulled in toward the beach, where the landing is greeted by a group of photographers and workmen. The balloons are removed as the cable is hauled ashore. At the same time, workboats and other ships offshore remove the balloons supporting the cable on the water. The The balloons are rounded up for storage aboard ship. The laying of this shore-end cable continues through the evening and into the night. By early morning, operations completed, the ship starts moving southward toward Guam on the final link of the 5,300-mile route from Honolulu to Japan. Moving along her course at a steady speed of 8 knots, the long lines completes the final splice off Guam some 12 days later. The new cable is officially opened for service by Frederick R. Capel, chairman of the board of American Telephone and Telegraph Company, talking from London on a three-way conversation with Douglas Guild, president of the Hawaiian Telephone Company, and Katsujo Ono, president of Kokusai Dinshin Dinwa Company Limited, the other two partners in this international communications project.
This is Fred Capel in London. On behalf of the men and women of the Bell system, my thanks to both of you and all of your associates. Tonight, we have seen two great countries move closer to one another. And by your partnership and cooperation, we've created a powerful instrument for worldwide conversation and understanding between people everywhere. It's been a great pleasure to participate in this occasion. I now declare the cable officially open for service between the United States and Japan. Good night, and my very best wishes to everyone who has participated.
Finishing her Transpacific venture, CS Long Line sails east to Honolulu to take on another load of cable. Then moving out toward California, she starts work on a second underseas telephone cable between Hawaii and the U.S. mainland. Some 2 weeks later, the ship stands off the California coast near San Luis Obispo to complete operations at this U.S. cable terminal. The cable is pulled ashore on the last few miles of its route. Then it is hauled through a trench in the beach and worked slowly and carefully by hand up and into a conduit leading to a manhole, where it is spliced to cable already in place from the terminal station. Proceeding up to San Francisco, the long lines ties up with the transport ship Scarva to load cable. This cable will link the Philippines to the Transpacific route at Guam. With her cable tanks loaded again, the long lines returns to Guam and starts out on the 1,500-mile route to the Philippines. Near the little coastal town of Bel Air, shore-end operations get underway. As the cable is floated in, work operations are also proceeding at the landing site. Excitement over the event runs high as school children from Bel Air are granted a holiday to watch the operations. Marching down the beach like a small army, they arrive with happy faces and welcome signs. Rope barriers are necessary to keep the enthusiastic youngsters out of the working area. Skin divers from the Philippine Navy are on hand to assist in the landing work. Now, as the cable comes ashore, it rounds a sheave and moves along the cable trench into the jungle. There it is spliced to another cable connecting it with the terminal station. Finishing the Philippines project, the long lines recrosses the Pacific to enter the Panama Canal. Crossing the isthmus, she moves back into the Atlantic on her way to Baltimore to pick up more cable and repeaters for her next assignment. A cable from Vero Beach, Florida to St. Thomas in the Virgin Islands, which she completed in December 1964. Another job completed, officials of AT&T and France's PT&T now discuss the final plans for the CS Long Line's next project, which is a fourth transatlantic telephone cable extending from the U.S. mainland to France. Beach Haven on the coast of New Jersey is the takeoff point for the 4th Transatlantic Cable. Lying offshore, the CS Long Lines maneuvers into proper position to lay the shore end portion of the cable. The captain zeroes in on the shore target and gives the order to begin operations. Contact is then established with the director of shore operations to inform him that the cable end is about to be started in toward shore. As the cable end is overboarded, it is picked up by a tugboat, which will tow it in toward the beach. At regular intervals, balloons are attached to the cable so that it may be floated in rather than dragged across the shore bottom. The bright orange balloons appear to form a brilliant dotted path from ship toward shore. A small boat coming out to meet the tugboat brings a tow line, which will be attached to the end of the cable. When the shoreline is secured, the tugboat cuts loose its tow line, allowing the cable end to slip into the sea. A cluster of several balloons suspends the cable end and marks its progress as it is pulled into the shore. Shore end operations completed, the CS Long Lines heads out into the Atlantic on the first leg of its ocean-spanning voyage from New Jersey shore to Saint-Hilaire-de-Rez on the coast of France. Cable tanks empty. The cable end is buoyed and marked, and the ship heads for her next cable supply point, Nordenham, Germany. While in transit, the conference table becomes the center of action where final plans are checked and discussed. At Nordenham, the cable has been placed in storage tanks and conveyed to the loading area, where it is put aboard the CS Long Lines. While loading proceeds, the shore end portion of the cable at Saint-Hilaire is being placed by the French. The terminal station is about 3/4 of a mile inland from the shore, so it was necessary to run a buried cable line down to the beach. Here, groups of men anxiously await the beaching of the cable end so that it can be tied to its land termination. Offshore, the French cable ship Marcel Bayard drops anchor and makes preparations for the placing of the shore end of the cable. On the foredeck, balloons are attached to the cable end, and it is overboarded. Then picked up by a small launch which will tow it to the beach. The familiar line of balloons marks its progress shoreward. Once the cable end is beached, it is spliced to the land line, completing the shore operations. Meanwhile, the CS Long Lines, having completed laying the cable picked up at Nordenham, stops now at Calais, France. Here, the large cable storage pans are transported on huge flat-bedded trucks from the manufacturing plant to the loading area and put aboard the ship. When she has placed these last miles of Transatlantic Cable Number 4, she will have compiled a total of 17,000 miles of cable placed in just over 2 years of service. A record of achievement unparalleled in cable ship history. On September 15, 1965, Transatlantic Cable Number 4 was officially opened for service, completing the latest link in this worldwide network of underseas cables. Around the globe, man reaches out to communicate with his fellow man. In future years, global communications will play an increasingly important role in the handling of personal, business, and governmental matters. This vast worldwide communications network was built through the cooperation of many nations and is dedicated to providing the best possible service for its customers. Beneath the sea, a constantly expanding international network of telephone cables, put there by men and ships like the CS Long Lines.